Hello, in this video I will be showing you how to use parameters to create a lift coefficient versus angle of attack graph for a 2D airfoil in Ansys Fluent. Alright, so first we're going to need the points in order to generate the CAD for our airfoil. And to do this, we're going to go to airfoiltools.com. This is a very useful website for pretty much any information you need about any airfoil. So for this demonstration, we're going to be doing a NACA N2414. So we're going to go down to N. Scroll down till we see NACA 2414. And just so you know, this is going to be the graph we're going to be trying to generate. This CLV alpha. Alpha is the angle of attack. Alright, so what we're going to do is we're going to click Send to Airfoil Plotter. We'll stick with a chord of 100 millimeters, but you can change that if you want. And then we are going to click CSV file of coordinates, and that will download. Alright, so next you're going to open up the CSV file from Airfoil Tools in your spreadsheet editor of choice. I will be using Excel for this example, and we're just going to be cleaning it up so that your CAD software can read the points for the curve. So as we can see, the Airfoil Tools has spit out a bunch of coordinates that will draw out the airfoil for us. So what we're first going to do is get rid of these rows. And then we're also going to get rid of the points for the camber and chord lines. We're also going to get rid of this row right here. And finally, we are going to get rid of the bottom row because it's the same as the top. And SolidWorks does not like it when you have two overlapping points. We're also going to add a third row of zeros because SolidWorks is expecting X, Y, and Z coordinates. And the very final step before exporting this file is going to be to make sure that all rows have the same number of decimal places. So then we are just going to save this as, you're going to go here and you're going to save it as a tab delineated text file. Alright, so now you're going to open up your CAD package of choice. I will be using SolidWorks, but if you are using something different, you might just have to look up how to do this on your own CAD package. First, we're going to go down here and make sure we are on the correct units. In my case, I'll be using millimeters. And then you are going to go Insert, Curve, Curve through XYZ points, Browse, Text Files, and you're going to select the text file we just created. As you can see, it is populated with all the coordinates from that file, and we're going to click OK. And as you can see, it has brought the shape of the airfoil in for us. So next we're going to go Sketch, choose the plane that the file was generated on, Convert Entities, and this isn't ready quite yet. We're going to now go and close this off right here so that we can then go and extrude it. And it doesn't matter how far you extrude it because we are going to be doing a 2D simulation. And now we have CAD for our file that Ansys can use. So now we're going to go up to Save As a step AP214 file. And now we will move on to Spaceclaim. Spaceclaim is going to be used to prepare our files to be put into Design Modeler in a minute. And so what we're going to do is we're going to go to File, Open, select the step file that we just created, and as you can see, it's imported. And now we're going to go over to Repair, and this is just going to be used to make it easier for the simulation to run. We're going to check Stitch, Gaps, Missing Faces, Split Edges, Extra Edges, Duplicates, Small Faces, Simplify, and Inexact Edges. Now, as we can see, Simplify has brought up that there is one spline face, and you're just going to click that face or the check mark, and as you can see, Spaceclaim can't simplify this edge, but we're fine in this case. This is going to be a very simple simulation, but if you have something more complicated, you may have to spend more time trying to actually fix this issue. So next we're going to go up to File, Save As, and we're going to save this as a Spaceclaim file. This is what we will use to import into Design Modeler in a minute. So save. Alright, so now you're going to open up Ansys Workbench. The version I'm currently using is 2024 R2, but this generally is going to stay the same. There's not really that much changed on the front end between the different versions of Ansys. So today we're going to be using Fluid Fluent. So we're going to go to Geometry, Design Modeler, and you're just going to give it a minute to load. Once it's loaded in, as always, check your units to make sure they're correct. We're using meters. And then you're going to go to File, Import External Geometry File, and you are going to go down to All Files and pick that Spaceclaim file from earlier and hit Generate. Anytime you have this lightning bolt here, that just means that Design Modeler is waiting on you to generate, and pretty much anything you do, it will ask you to regenerate the geometry. So we're just going to give it a second, and here we can see that our file has been generated. And next we're going to change our view to this one. We want to create a sketch on the XY plane. Sketch. And then we're going to go to Sketching. We're going to create a rectangle, which will become our flow domain. Dimensions. You're going to need to create these 4 dimensions right here. These L4 and L2 are going to be used to create the size of the flow domain, and L1 and L3 are just going to be used to position it correctly. So what we're going to do is, in a simulation this simple, you can just eyeball it. But in a more complicated solution, you may want to spend more time on this step in order to decrease your computation time and to ensure more accuracy. So this looks about good. From this tab, we're going to go up to Concept, Surface from Sketches. We're going to choose our sketch, add Frozen, and then you're going to hit Generate. So that's going to generate our flow domain. Next thing we're interested in, we're going to create a new sketch on the XY plane. And this will be a smaller rectangle that will be used to increase the density of our points when we go to generate the mesh. So we're going to do the exact same dimensions again. And once again, I'm just going to eyeball this. And that looks about, or actually I'll decrease this. So that looks about good to me. And once again, we're going to go Concept, Surface from Sketches, select our sketch, Apply, Add Frozen, Generate. Now our next step is we are going to go to Create, Body Transformation, Rotate. We're going to select our airfoil. For our axis, we are going to select the Z axis. A lot of times it's easier to just go into here and change this to components and go 0, 0, and in this case we're interested in the Z axis. We're going to leave this at 0 for now, but we are, or 45, but we are going to click here and create a parameter, and I'm going to name this alpha to match the graph on airfoil tools. Okay, and this will just allow us to change it as a parameter later. And I'm going to hit generate, and when we it doesn't matter that it's at this angle right now. We're going to change that in a minute anyways. So our next step is going to be create, go to Boolean, and we want to subtract. We're going to select the flow domain is our target body and our airfoil as our tool body. You do not want to preserve the tool body, and you are going to hit generate. Now the final step is going to be to create our named selections. So you're going to go up here, you're going to select this is going to be your inlet, and naming it this makes it easier because Ansys Fluent will go ahead and when we get to the setup we'll recognize that this is an inlet. We'll go here, hit apply, name this outlet, generate. These two right here we're going to name sim. For our airfoil, we are going to create a named selection wall. I like to create a named selection as well for the fluid domain. And then finally we are going to create a named selection for our small domain here, which I will just call small. And once again you're going to hit generate, and once you've done that you can just exit out. So now as we can see there's a check mark for geometry telling us that workbench has accepted the geometry. We're now going to go to mesh and we're going to edit, and you're going to give it a second to load up. Now once it loads we're going to go into mesh, we're going to insert a method, we're going to select our large flow domain, and in my case I will be using triangles, but depending on your application you may use any number of the other ones. I'm also going to go into mesh, I'm going to add an inflation layer. For the geometry you're going to select the whole domain, named selections, and for the boundary here we're going to select our wall. I like to do a growth rate of 1.1, and in this case I'd say maybe 12 layers to start. And this is going to be kind of an iterative thing. You may find that your mesh is not accurate, then you need to come back and change some of these settings. But the last thing we're also going to do is we're going to select sizing. We're going to go down to type. We want to do a body of influence. Once again, for our geometry, it's going to be this whole area. But for our body of influence, it's going to be that smaller rectangle from earlier. Then we're going to go up to connections, delete your contacts because we don't need them for this simulation and they're just going to get in our way. And then hit generate, and as you can see, it has created this mesh for us. Now you're going to see why we included these. I want this area right here to have more elements. So it was automatically set to 0.18. We'll set it to 0.15. And we'll check the mesh again. I would still say I'd prefer to have some more this close to the airfoil. So I'm going to go into here one more time. 0.12. Generate. I'll also change this growth rate right here. Generate. And that, I'll say that'll be fine for the purposes of this simulation. So once again, just like Design Modeler, you can just X here. And you're going to go to Mesh, and you're going to hit Update. And you're just going to let it update. Now while we wait on that update to complete, I'm going to real quick show you very quickly how to do the Reynolds number calculation for this simulation. Specifically, we're interested in getting what speed we will want to use to get our specific Reynolds number. In this case, I'm shooting for a Reynolds number of 100,000. I have a full video going over the Reynolds number, which I'll link in the top corner of the video. So we're using air at 20 degrees Celsius. At that temperature, air has a kinematic viscosity of 15.06 times 10 to the negative 6 meters squared per second. Once again, we're shooting for a Reynolds number of 100,000, and our chord length is 0.1 meters. So just plugging it into the Reynolds number formula, we are going to get that we are going to want an inlet speed of 15.06 meters per second. Now once the mesh is done updating, you should have a check mark at mesh and the symbol again for setup. It's always a good idea to go ahead and save your work. You can just do that by pressing Control S. And one thing I wanted to note before I go to setup is notice that there is one arrow coming from parameter set into parameters. That is because of the parameter we set up earlier, the rotate. And soon we are going to have another arrow coming out from parameters down to parameter set, and that will be for our coefficient of lift, and we are going to set that up now. So we're going to go into Setup, Edit. This box will come up. I always select Double Precision. And since I'm using the student version of Ansys, I have a maximum of 4 salt verb processes. And we are now just going to allow this to load. You will know Fluent has loaded when your mesh is displayed and the console stops adding new commands. So our first step is going to go to Boundary Conditions, Inlet. We're going to select our inlet name selection that we created earlier. We're going to put in 15.06, which is the velocity I calculated earlier, but yours obviously might be different depending on the airfoil you're using. Hit Apply and Close. The rest of our name selections should be okay just as they are. Next we're going to go to Report Definitions, and we're going to create that parameter, that new parameter. We're going to go to Force, Lift. We want the lift coefficient. We want the lift coefficient on the wall, which remember is the edge of the airfoil. We're going to have 1 at Y, 0 at X. This is just the magnitude of the report in each direction. Z is grayed out because we are doing a 2D simulation. I like to select Print to Console just so that I can see what it's doing. Then we're going to do Create an Output parameter. That's going to create that new arrow and allow us later to use this number in creating a graph. And we're going to hit OK and close. Next we're going to go into Initialization, hybrid initialization, and you're going to hit initialize. And then you're going to go down here to run calculation, and you're going to set it at 500 iterations and hit enter. And now you can exit out of Fluent. So now we have a check mark next to setup, and we can go into our parameter set, and we are going to create our parameters that we want to run through. So I'm going to go from -10 to 10 at increments of 2.5. You can do more increments for a more accurate graph, or you can do less. You can do a greater range of alpha values, but I'm going to go through and do these values. And I'm going to hit retain. And now you can go back over to here, and you're going to hit update all design points. And now what Fluent is going to do is it is going to run through each one of the parameters we set up, and it is going to redo the geometry, redo the mesh, and redo the setup. And this may take a while depending on how complicated your mesh is. I did a relatively simple mesh, so this shouldn't take long, but I will come back when it is finished. You will know your simulation is done running when you go down to show progress and there is nothing happening. While it is running, it will tell you what it's doing right here, and it will give you a progress bar to completion, and it will also give you a little X that you can use to abandon if you realize last second you forgot to do something. You will also know because this down here will go from busy with a red dot to saying ready with a green dot, saying that it's ready for your next command. At this point, it is always a good idea to save your work. Once again, that can be done with Control S. And now you're going to go over to parameter sets. As you can see, here's all our data points, and I did add a couple just to make it easier to compare to airfoil tools. I added -15, -12.5, 12.5, 15, -17.5, and 17.5. So what we're going to do now is we're going to go over here and double click on parameter chart. That will create a new parameter chart for us. For bottom, we're going to select alpha. And for left, we're going to select our coefficient of lift. And then we're just going to click here so we can see. And this is the graph of all of these points that we generated. And as we can see, if we compare this to airfoil tools, which this is at a Reynolds number of 100,000, just like we're using, we can see we are getting that same sort of shape, just reverse, which we could change this if we just reverse the direction in setup, but we are getting that exact same shape. So anyway, this is how you can set up a coefficient of lift diagram in Ansys Fluent. The same process could be used for coefficient of drag versus the angle of attack. You would just use the coefficient of drag instead. And if you have any questions regarding this process or any suggestions for future videos, please leave them in the comments. And anyways, thank you and have a great rest of your day.